to learn about binomial expansion. Maybe you're a year 11, just about to start year 12. Maybe you're a year 12 who has done it so far. Maybe you're a year 12 who missed out on it because of lockdown. Maybe you're a year 12 who did it but was like, what? So any of these things, maybe you're a year 13 revising. Whatever has brought you to the channel either live or later on, I hope that this short video will help introduce the binomial expansion. I'm going to stop short of doing negative powers and fractional powers. I will do a second follow-up A-level video on negative and fractional binomial expansion powers. But but I will try and remember how to speak. But for the time being, let's get straight into the intro. So, the binomial expansion. I'm going to start off by going straight over here and introducing something called Pascal's Triangle. Now, Pascal's Triangle is used, but not necessarily known that it's used. If I was to expand this, x plus 1 to the power 1, you will notice I get one lot of x and 1. If I expand x plus 1, I actually will get one lot of x squared, two lots of x, and 1. If I expand x plus 1, x plus 1, x plus 1, I will eventually get one lot of x cubed, three lots of x squared, three lots of x, and 1. And in fact, if I do x plus 1 to the power 0, I also get 1. Extrapolating just the coefficients, you get 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And you can always find the next number down by adding the pairs. 1 on either end. Those make 4, 6, 4. So that would be the next pairs of coefficients if I was to do x plus 1 to the power of 4. And I can extrapolate this down 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1, 1, and it'll always be symmetrical. 1, 7, 21, 35, 35, 21, 7, 1. But it would be useful if we wanted to do, for example, x plus 1 to the power 10 to not have to build the entire table. So a method of getting these numbers is useful. And to do that, we use nCr on the calculator, which is going to be the number which is the power, so in this case 10, and then C, which stands for combinations of choose, 10 choose 4 would be, just to show you, 7 choose 3 is going to be 7, 0, 1, 2, 3. Is 35. There are 35 ways of choosing 3 items from a list of 7. And that's what this means. It is calculated by doing n factorial over r factorial n minus r factorial. So 7 factorial over 3 factorial 4 factorial, because 7 minus 3 is 4. Remember, factorial means times everything, so 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 4 times 3 times 2 times 1. Now the reason that's useful is those 4 all cancel with those 4. And the 3 times 2 cancels with the 6, and you'll notice it is indeed 35, which is what I said it would be. So therefore, 10C4 we can calculate on a calculator, but we can also calculate by saying it's going to be 10 factorial over 4 factorial, 6 factorial, because it'd be 10 take away 4. So we can use that to realise that the top line will be 10 times 9 times 8 times 7, but the 6 times 5 is going to cancel with that. So it's going to cancel everything else. And then this is going to be 4 times 3 times 2 times 1. And I believe 4 times 2 is 8, so that cancels. And I believe 9 cancels with the 3, leaving us with 10 times 3 times 7, which I believe is 210. So we know that I already know that it's going to be one lot of x to the power 10 plus 10 times x to the power 9, you'll notice they all start 1, then the number itself. But I also know that the term in to the power of 4, so it'll be the fourth one along, it starts with 0. So it'll be 0, 1, 2, 3, so the one with x to the power 5. 1, 2, 0, 1, 2, 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. I think it's there. I'm being a fool. 4 cube from you. Let's just get rid of those so they're not messy. So I think it's going to have 210 x to the power 6s. Okay, and this is a way we can work out the whole expansion. So if we were doing this for any expansion we want to do at all, we would do x plus 1 to the power of say 8. We would need to do 8 different things. Now for each one we're going to do 8c1, 8c2, 8c3, 8c4. The next thing we're going to do is we're going to do x to the power 8, x to the power 7, x to the power 6. Now you'll notice how I lay these out. I put them in a line. This is because the coefficients are easier worked out, I think, by lining them up above each other. Then we have 1 to the power 0, 1 to the power 1, 1 to the power 2, 1 to the power 3, and so on. Your calculator will give you that this is 1, 8, and then it will give you the other ones. And if you look at the test card, you will see, I can't remember where I've put my calculator, just to be helpful. I will have put it somewhere safe, because that's where I put things. 2 seconds. I probably took it to school, so I imagine, here it is. I want to say 56, but let's just confirm that. 8 nCr. There you go. 8c3 is 56. It's like I've done this before. 8c4 Now, the observant amongst you will have realised they're supposed to start at 0, not at... It's because it's a hot day and it's very hot in this room, and I've had to turn my cooling fan off. It's very... so it's 1, 8, 28, 56. I was right with the 56, but missed out 28. Okay, so this is... and then for each term, you times them all together. So 1 times 8... x to the power 8 times 1 is x to the power 8. This will be 8, and obviously the 1s make it quite straightforward here. But you'll see when I do the next one that having this approach with 1, you don't get to really see why this approach is useful, and you would go all the way down. Now the reason this approach is useful is when you've got something like this. So it could be 2x plus 3 to the power 5. Now we could expand the brackets manually, but they would take us a long time. And this method allows us to expand the brackets to this very, very fast. So I know I'm going to need 5c0, 5c1, 5c2, 5c3, 5c4 and 5c5. So I know there's 6 terms. I will leave a space for what those numbers are. I know that's going to be 1 and 5, 1 and 5, and I think if we remember back earlier it was 10, 10. Now, the next line, so that's the nCr line, the next line is going to be the x line, we are going to have 2x to the power 6, 2x to the power 5. And there's a specific reason you must do these in a bracket. And that is that if you do not do these in a bracket, then you forget 0, 1, 2, 3, 4, 5, 6. It's 5. I don't know why I started at 6. That'll be why. The smoothness of trying to do a live video rather than trying to do it and cut it. I'd have been starting again, I think. Okay, and then the other one is the 3. The 3 is just going to be 3 to the power 0, 3 to the power 1, 3 to the power 2. Now your calculator will give you all these values, but the reason I do it like this is because I think it's very useful to then be able to go, so with these are the NCR values. This gives us 5 to the power 2 is 32, x to the power 5, 16 x to the power 4, 8x cubed, 4x squared, 2x and 1. And this is going to give me 1, 3, 9, 27, 81 and 243. Now the reason this is useful doing it separately is because then the actual terms you want, so the 2x plus 3 all cubed, you just times everything together. So I've got 1 times 32 times 1 is going to be 32x to the power 5. It goes straight to the right terms. Then we've got 5 times 16 is 80 times 3 is 240. It gives us an immediate way not only of tracing mistakes, but also we know it's that coefficient, and that coefficient all times together. 10 8 are 80 times 9 is 720. X to the power 3's. This one is 10 4s are 40 times 27. So 4 27s are 104. 40 27s will be 1040. X squared. And you can see you would not want to be manually working these out. The binomial expansion allows us to work this out very, very quickly. Then 5 2 is 10 times 81 is 810. And then 243 on its own. Now the reason this is useful is we could then very, very quickly know what, like if we were trying to put numbers in. If I wanted to do, for example, work out what 3.6 is to the power of 5, and I was trying to do this manually, you could break this 3.6 using the binomial expansion into that's 0.6, so x is 0.3. So you could do 32 lots of 0.3 to the power 5 plus 240 lots of 0.3 to the power 4. Now, progressively, that is how a calculator would go about, possibly, a longer calculation like that. But it would do it all obviously behind the scenes. What we're trying to do is realise what the x term. A lot of A-level questions will say, what is the term in x to the power 5? What is the term in x to the power 4? And you might only be asked what the first 3 are, or you might be asked what a specific coefficient is. So you see a lot of A-level questions which are like, what is the coefficient in x squared? So it might say, if it says what's the coefficient of the x squared term, what you're going to do is realise you just need that term. So let's say the question then, we get an A-level question, it says, in 3x plus 5 to the power of 7, what is the x cubed term? So we're going to look at this and go, well, how do we get the x cubed term? Well, to get the x cubed term, we're going to need 7c something. Then we're going to need something that gives us the x. So it's going to be a power of 3x, and then it's going to be a power of 5. Now, the only way to get x cubed, it must be 3x to the power 3, right? We also know that that power there goes gradually down while the other number comes up. So this must be 7c4 to make up to 7, and this must be 5 to the power 4, because that gives you the x cubed power, and those must add to the 3 to make the 7. So we've got the total. That allows us to use the calculator specifically for one term. 7c4. I use shift divide on my calculator, and it gives me 35. And 27 x cubed. And 5 to the power 4 is 625. So we get 35 times 27 times 625 is, and you do get huge numbers here. Don't be put off by the fact the answer here is not 590,625 x cubed. But that would be the final answer to what is the thing. Now I don't know if that is all fitting on the screen, and I think it's important that it all fits on the screen. So I'm going to select that and just move it over a bit so we can all see what's going on there. So that is how we use the binomial expansion and perform the binomial expansion. Each time you've got to use nCr. The number for r will be the power you don't want. So if I'm doing the x cubed term, I do 7c4, 3x to the power 3, and 5 to the power 4. You can also do it so it's the same because of the fact that they mirror each other. You could have done 7c3 and it would also give you the same answer. So we could use the same number there as well. So it doesn't matter which one. I just go with what I prefer. But we could use 7c3, 3x to the power 3, and then 5 for because it's the other bit. So the other bit uses the leftover power. That's possibly easier to think of it in terms of counting down the powers rather than counting up the powers with your 7c's. So because of the nature of the fact that these are symmetrical, you can do it the other way around as well. So you can do 5c5. And if people are learning this for the first time or trying to remember it because they get confused, it's possibly easier to keep the power number the same as the term number. 2, 1, 0. Okay, so hopefully that's useful. I hope that has helped you a little bit to start doing the questions. The next thing you need to do is go away and do some questions on the binomial expansion from your A-level textbook, and put any message on the video at the bottom in the comments. I will try and help with. If anyone's stuck on a question, they're working at home and they're stuck on a question and they want to get in touch with me instead of the teacher, that's absolutely fine. I'm more than happy to help anyone from any school, anywhere. Just let me know. It can be anywhere in the world. It doesn't have to be UK, but just send me a question on here, or if you look on here, I've also got my email address on there. I think it used to be on there. Yeah, email address on there if you want to ask a specific question. So hopefully that's been useful. I've been Mr. Harris in a very muggy office. Hope that you've helped understand a little bit about the binomial expansion. I've been Mr. Harris. You haven't. Look after yourself and take care.